Welcome to a Chemistry of Water lecture in which we are talking about the unique properties of water based on its peculiar chemistry and how that impacts the biological world. So, first off, quick review of water's capability to make hydrogen bonds. So remember, hydrogen bonds are bonds between hydrogen and electronegative chemicals. Water is two hydrogens and an oxygen. Oxygen is highly electronegative. So we've got oxygen, we've got two hydrogen. These hydrogen, due to bond angles, are projected, let's just say, below our oxygen molecule. And thus, when oxygen's electronegativity hogs hydrogen's electrons, oxygen ends up with a partial negative charge, and each hydrogen ends up with a partial positive charge. So, this means that we have something electronegative that is also negatively charged, or at least partially negatively charged, and thus it can attract hydrogen. And the hydrogens in a water molecule bearing that partial positive charge are particularly apt to make hydrogen bonds. So, when we have multiple water molecules together, they will form hydrogen bonds. And that will cause water molecules to stick together. So, we got hydrogen bonds forming between the hydrogen and the electronegative oxygen. This is pretty consequential. This is essentially what gives water its unique properties. This hydrogen bonding is going to be directly responsible for all of water's unique properties. Hydrogen bonds, interestingly enough, are very weak bonds. Without a strong covalent bond connecting them, or even the electrostatic forces of an ionic bond holding them together, these bonds are just attraction, right? So when we say a bond between hydrogen and electronegative chemicals, we can say attraction, to be pedantic about it. And this attraction, it's capable of being broken. Hydrogen bonds can break and reform constantly. In fact, when molecules of water are moving around in a liquid environment, they are constantly moving around. And when they get close to each other, they'll hydrogen bond, but then they'll continue on their way and break the hydrogen bond. So, hydrogen bonds are weak, but they are extremely important, both to the chemistry of water and to biology as a whole. So, as I said, we have our hydrogen bonds forming between water molecules. This property of water sticking to itself via hydrogen bonds right? This is called cohesion. And cohesion produces a number of the properties of water. So, when we talk about water, there's four fundamental properties that we want to talk about. Water's cohesive nature, that's going to have multiple consequences. Water's capability to moderate temperature, the fact that ice floats, and water's capabilities as a solvent. So, first off, cohesion. Again, water molecules, hydrogen bonding to each other and sticking together. This produces two important things to talk about. One is adhesion, and two is surface tension. So cohesion is our introduction to talking about these two important properties of water. So first off, adhesion is the hydrogen molecules in water sticking to other substances. So H2O sticking to other substances. Substances. That's good enough. H2O sticking to other substances. And remember, this is hydrogen bonding. So what that means is that water molecules, the hydrogen in water molecules can form hydrogen bonds to other substances, not just other water. And so this means that the substances water sticks to have to be capable of forming hydrogen bonds. And that means they have to have some kind of charge. So if I'm talking about charge here, it's important to refer back to the concept we talked about in polar covalent bonds, and that's polarity. So let's just really quickly mention polarity and the ability of water to hydrogen bond to polar molecules. So when we say water is capable of sticking to things or adhering to things, we mean it forms hydrogen bonds to polar chemicals. Polar just means that we have a positive or a negative charge, and it doesn't have to be fundamentally polar, right? So for instance, sodium chloride is a bond, an ionic bond, and it consists of a sodium cation and a chlorine anion. Those are fundamentally polar compounds. All ionic compounds are fundamentally polar. But there's a lot of compounds that might have, polar regions. So small regions of polarity. And as long as it has polar regions, it can bind to water. So it just needs to have some kind of polarity, right? It could be polar fundamentally, or it could have polar regions. Either way, water can bind to these chemicals. Anything that we say is polar or has polar regions gets to be called hydrophilic, right? Polar, and water can form hydrogen bonds to it. So, not too terrible. As for a chemical that water cannot form hydrogen bonds to and thus cannot adhere to, we call those hydrophobic. And they are non-polar chemicals. So when you look at them, they have no polarity in them. So even if they have like an electronegative component, perhaps the way the molecule is organized prevents that electronegative component from causing a polar region. So it gets complicated. But either way, it's nonpolar, and so we cannot form hydrogen bonds to nonpolar chemicals. So that's pretty cool. And we'll get right back to talking about adhesion, Well, I guess we've already talked about adhesion. Right, you're familiar with adhesion from water's capability of sticking to glasses, especially when you're trying to dry a glass or a plate. You might think you've completely dried it off, but wait a minute, and there's water collected in the bottom again, and that's because small amounts of water adhered to it. Another consequence of water adhering to other substances is the meniscus. So this has to do with water in tubes. So any kind of container that you have water in, here's a graduated cylinder. When water is in that container, it will adhere to the sides. And it will actually adhere a little further up on the sides than where the water sits. So we call the bottom of this the meniscus. This is very important when talking about measurements during the lab, but it's also pretty fascinating because the meniscus results in some very fascinating physics of water movement. As the diameter of a container decreases, the meniscus becomes more drastic, right? It adheres further and further along the sides until you get to a container that's diameter is so small that there's no meniscus at all, and water just adheres to the sides and keeps adhering and ends up pulling itself through the container. As it adheres to the sides, it continues to adhere to the sides, and it will flow out of the container if the container's, hollow. If you've ever been in a healthcare setting, they'll use little tiny glass tubes to collect blood for doing a blood test. And that tube is just taking advantage of this fact that liquid, blood is a liquid and it's mostly water. And so it adheres to the sides. So this feature of water that allows it to pull itself just through the physics and chemistry of water, to pull itself through tiny tubes, is called capillary action. Capillary action is a consequence of water's capability to adhere to substances around it and being hydrogen bonded to itself, right? So because the adhered water pulls itself along the sides, and because the water molecules are hydrogen bonded to each other, they pull all of each other through it. So that's pretty darn cool. Trees and plants in general make efficient use of capillary action. When you look at a cross-section of a plant, say the stem, because that's nice and large, you will find near the center itty-bitty holes. These holes are very small in diameter. You'd need a very thin section of the stem and a pretty powerful light microscope to even see these holes. Really, the only way to get good detail on them is with electron microscopy. These things are very small. We're talking 100 nanometers in diameter, so very small. My frog is distracting me as he is chatting away. I have no idea if he's audible. I think the microphone scared him. Yeah, we'll try and catch him the next time he does it. His terrarium, as you can see, is quite the rainforest, so we're probably not going to be able to get a view of him, but he's adorable. All right. if you look at the course homepage, that's the leopard frog right in there, CC Dubs. He's clearly pictured in the course homepage, and he's the picture for the course in dashboard. So that's pretty cool. All right. I'll talk about trees in a minute when I talk about surface tension. So capillary action will come up again. Here's some cool instances of adhesion, right? So when we talk about water sticking to substances, we often talk about dew. So dew forming on things is a great example of water's capability to adhere to things. If you set out like a thin piece of wax paper, you wouldn't get near the amount of dew as you do with things that are nonpolar or polar. All right, very cool. There's, the water pouring out of a glass that you thought was completely dry. All right, next up is surface tension. Surface tension, simply put, is a concept in physics. So this is liquid physics. It applies to all liquids. And essentially, surface tension is the energy required to break the surface of a liquid. So, in general, a higher surface tension means that you have a greater resistance. So, takes more energy to break the surface. And also, that means the liquid surface stretches much more. So, the surface can stretch before breaking. To anyone who has ever done a belly flop, you may recognize that water has a crazy surface tension. It's obviously not the greatest surface tension of any liquid, but liquid water has a surprisingly high surface tension. And once again, that's due to our hydrogen bonds. Hydrogen bonds between water molecules help them stick together, so that when something tries to break the surface, the hydrogen bonds are helping water molecules stick together, and so they stretch. The surface is going to stretch, but not immediately break. That's why when you hit a large surface area of water, you're hitting more water molecules, hydrogen bonded together, and so it can feel like hitting a solid surface. That's just because you're trying to break more water molecules in one instant. Like if you were to take your finger and point it down into the liquid, it breaks the surface relatively easy. But if you try and slap it with the flat of your hand, you can get a really nice loud crack. And then if you do a belly flop, you can end up with your entire front reddened and sore because it was extremely uncomfortable. So you get high up enough, and when you hit the surface of water, regardless of what kind of pose you're in, it can kill you. Jumping off the Golden Gate Bridge in San Francisco was a common method of suicide. And it was surprisingly effective as far as jumping because you were really high up and there was water below, and very few people survived impacting the water, and they got a quick and final introduction to the surface tension of water. So, cool pictures of living things exploiting water's high surface tension. Here's some fun little water bugs. There's a paper clip. If you can get a paper clip small and thin enough, and you're very gentle with your hands, it's possible to float a paper clip on the surface of water because surface tension. There's a fun little water spider. Even spiders are capable of running across the water. And then here's one of my favorite pictures. This is roughly a nickel-sized coin. And you have a high frame rate camera, and they dropped that coin into water. And you can see that we're roughly, I don't know, 2 nickels deep here. And the water surface is just stretching. It hasn't broken yet. It's still just stretching. So that's because water has that great high surface tension, and that's because of all those hydrogen bonds holding water together. So let's talk about surface tension and adhesion in biology. And we're going right back to plants. So here are those holes in the center of a stem that I was referring to. So these are very thin holes. I still haven't fixed the bullets, but honestly, I'm going to explain this just fine. This is capillary action in biology. So plants do not have a pumping structure to get water from the roots through the rest of the plant. Water for plants is absorbed in the roots. And so the only way to get that water through the plant is good old capillary action. So you have your tube that is thin enough that water is pulled through it. And so adhesion, right, allows this water to stick to the sides, as I talked about during adhesion. And it's thin enough that we don't have a meniscus forming. It just keeps pulling itself up the sides. This is a tube with an opening here. And the surface tension of water is what allows water to essentially suction itself through this capillary, right? So the surface tension, right, it basically allows the capillaries to suck water through the tubes. And adhesion is why this water goes all the way through the tubes, right? Travels all the way through. Surface tension also helps out water because the further high up you go, the more gravity is a concern. When you've got a thin passage and you're trying to pass water through it, right? There is a higher potential for gravitational energy higher up than lower down. The further up you get, the more you would be in danger of the water in this tube breaking. Right? If the water molecules couldn't hold themselves together and stick to each other, once you got to a certain height, they'd break. And once they break, adhesion becomes less useful because not only does it adhere to the sides of the capillary above it, but it adheres to the sides below the break as well. And so it's going to take a lot more, essentially, force to get that water to travel through there. So these capillaries in the trees and the plants take advantage of water surface tension. That surface tension, because it's thin enough, that surface tension is going to be strong enough to prevent these kinds of breaks in the fluid. And so it'll be able to travel all the way through the tree. Even if you've got one of those gigantic sequoias or redwoods, the redwoods get something like 200 plus feet. I think the record was almost 300 feet tall. And all the way up at the top, those branches and leaves are still being fed by water that's continuous with the passages that go all the way down to the roots. Right? So this is an extremely efficient use of water and the properties that hydrogen bonds give it. So that's pretty cool. All right. Now, let's talk about how water moderates temperature. So, to talk about how water moderates temperatures, we're going to first need to talk about physics. So, with the physics of matter, and it's kind of odd to say matter, so I will just start saying, I guess objects, although calling liquid water an object is kind of weird. So, how about things? Yeah. So, in the physics of matter, there is a concept called specific heat. Specific heat is defined as the energy required to increase the temperature of a thing. Now, for all you people out there who want to get pedantic on me, don't quote me, but I'm pretty sure you'd say the energy required to increase the temperature of 1 milliliter by 1 degrees Celsius. Right? In this case, our energy is, we're going to be talking about temperature moderation, so we're going to be talking about heat energy. If this were a physics class, we'd talk about the amount of, joules of energy that heat produces. So this is not a physics class. We're going to leave it at heat energy, and we're going to be happy about that. So, all right. And we're also just going to say increase the temperature of a thing. We're not going to talk specifically about the volume and the temperature. But specific heat is important to know about. The higher a substance's specific heat... Oh, substance. Wow. That would have been a really good word. I'm just putting it in there. And I'm going to pretend I had it that way the whole time, but I am not going to edit this. Anyway, the energy required to increase the temperature of a substance, and when we look at different substances, having a higher specific heat means it takes more energy to increase the substance's temperature. Various substances have various specific heats. The great example here that I do in class every time is a cast iron pan. So a good old cast iron pan made of, who'd have guessed, iron. Iron is known for having a very low specific heat. It's a great conductor for heat. Heat transfer works really well with iron. Water has a much higher specific heat. We'll just say high specific heat. And if you want to see that in action, all you got to do is have 2 cast iron pans, same size, right? There's my cast iron pans on the same oven, and I put both burners on, let's just say high. Harkening back to ye old experimental design, what we'll do is put a chunk of iron in this cast iron pan that has the same volume as the water that we'll put in the other cast iron pan. So here's my iron, and we'll put the same volume of water in this cast iron pan. I give this 2 minutes on the oven. 2 minutes. High heat. I come back and I say, hey, put your finger in one of those pans. And I don't know, I hold someone you hold dear hostage. You know, you're going to put your finger in one of those pans now, buddy. Or very bad things are about to happen. And which one do you choose, right? So, barring kink, you're going to choose water. And that's because after 2 minutes at high heat, your water is not going to be near the same temperature as the iron plug in the other pan. Because specific heat. Iron conducts heat super well. So the heat from the burner goes into the pan, goes into your big hunk of iron extremely quickly because iron heats extremely easily. It has a very low resistance to heating. The energy you put into heating, really easy. Water has a very high specific heat. Even though the burner is at the same temperature here, and the cast iron pan is going on the burner is going to heat up the same amount as the one over here, the transfer to water is not going to be nearly as quick. And the reason is, right, it's not that the water is getting less heat energy. The water is getting the same amount of heat energy as our iron plug. Right? They're getting the same exact amount of heat energy. There's not heat energy lost or anything. It's just the same amount of heat energy that it takes to warm that iron plug up to something that would burn your flesh off won't raise water's temperature that much. So after 2 minutes, it's probably pretty safe to pop your finger into that water there for a couple seconds without burning it. And that's just specific heat. It's taking the same amount of heat energy, but water requires more energy to increase its temperature, right? If you were a giant math nerd, you could say like 50 energy and like 300 energy for our made up numbers. And our iron pan, our burner is giving it like, I don't know, 1,000 energy. Whoops. Math's not going to math right. 500. Ha ha. So, if this is the energy and this is the specific heat, right? Just in our made up numbers thing, we could get our temperature increasing by, I don't know, 200 degrees over here. If this was just, 50 energy to raise by 1 degree, whatever. We're not even calculating volumes here. We're not doing it right. We're just conceptually doing this. Right? This might increase 100 or 200 degrees because you put 1,000 energy into it, and each 50 units of energy allows it to increase the thing by a degree. Over here, it takes 500 energy to increase the thing by a degree, so it only increases 2 degrees. Right? So this is our putting numbers to it for you numbers people. If you were fine on the concept until I put numbers to it, ignore the numbers. The concept of specific heat and how it works is way more important, right? You won't be tested on any kind of math. So, anyway, water has a very high specific heat. So water can absorb a lot of heat energy without changing its own temperature very much. Right? Water absorbs heat Let me find my erase the screen thing. Uh-oh. And kill sometime. So water is capable of, there we go, absorbing heat without significantly changing its own temperature. So water can absorb heat from an object without changing its own temperature, right? In other words, if there's water on my body, it could absorb, a degree of body temperature from me, and the water would not go up by 1 degree of temperature. That's just simple as that, okay? So, not awful. This allows water to absorb heat and then take the heat with it. So let me blank this slide because I want to talk about evaporative cooling first. So let's talk about the level of objects and critters, right? So we have some water sitting on a thing, and the water absorbs heat energy from the thing into the water, right? Whoop. Heat energy goes into the water. Now I have this water here containing the absorbed heat energy. And then my water evaporates. Off of the object. Right? Evaporation is kind of cool because in evaporation, it's not water in its gaseous state. It's liquid water. Again, that's pretty darn cool. But the water evaporates, and as the water evaporates, it takes that absorbed heat energy with it, right? And so my surface is now cooled off by the amount of heat that the water absorbed from the surface. We call this evaporative cooling. And in the world of biology, all you got to do is think of yourself and know a cool example of evaporative cooling, right? A cool example. Anyway, and that's sweating. When you sweat, right? When a human sweats, they sweat water onto their skin. And then the water absorbs body heat. And then it evaporates and the body is cooled. If you compare animals that sweat water and animals that sweat something else, then you're going to see that animals that sweat water have a much, much, much higher tolerance of heating than animals that don't sweat water. So, for instance, think furry critters. My dog Oscar, he's covered in fur, right? He has really dense fur. It may be short, but he has an undercoat in there too. So he's got a ton of fur. The keratin that makes up fur is brittle. And the only way to keep that soft and flexible is oils, right? It's why if you only shampoo your hair, and you never condition it, your hair is going to feel a little drier and scragglier than the people who condition their hair. And that's just a function of the fact that shampoo is soap. Soap strips oil out of your hair. The conditioner is literally putting oil back in your hair. That's the function of conditioner. Regardless of, I'm on a rant, but regardless of what the marketing says, all it does is put oil on your hair. You get rid of it with the shampoo, you put it back in with the conditioner. It's just, hopefully you feel cleaner with conditioner than your body oils. A lot of science, body scientists actually recommend washing your hair like once or twice a week, or even your skin once or twice a week for a different reason. And then just rinsing with water, or water in a washcloth the rest of the time, which is, I don't know, kind of cool. Anyway, end random information unrelated to evaporative cooling. But what I was trying to say is, with all that fur, my dog mostly has oil glands on his skin. Very few sweat glands to keep his fur nice and supple. This means that Oscar doesn't sweat near as much water as I do. If you put both of us in a closed up car on a hot day, Oscar's going to overheat way faster than I would, right? Oscar will overheat to lethal levels, and I will still be okay. Humans have a much higher capability of resisting heat because we sweat water. Pretty cool. Oscar does use water for evaporative cooling, right? The main source of water that he produces for evaporative cooling is saliva. So this is why in heat, dogs pant. They pant because they are producing excess saliva, so the saliva can absorb body heat from their mouth. And, panting is breathing, but increasing their breathing rate could also sort of help a little bit with evaporation of saliva. That's not here nor there. But the fact is that his mouth is one of the primary methods for evaporative cooling. All animals in heat will try to take advantage of evaporative cooling to some degree. It's just furry things basically have to use their mouth or die if the temperature is hot enough. So, evaporative cooling is very cool. And that's how water can aid living critters in maintaining body temperature. Now, we can also think of it at a much larger scale, because this is aiding the body temperature of critters. But when you talk about the planet, right, if you've got water, the ground and rocks and whatnot heat faster than water. And so water is going to absorb the temperature of the ground around it. It's also going to absorb atmospheric temperatures. And by this, remember, when I'm saying absorb temperatures, I'm being lazy. It absorbs heat energy from the ground and the atmosphere around it, and as it does that, it removes heat energy from the things it's in contact with, and thus they become cooler, right? So it's absorbing this heat energy. As long as the water is colder than what's around it, it's going to absorb heat energy. And then if you get into an area, let's go three-dimensional here. Ooh. Oh, yeah. Perspective. If you get into an area that is colder, right? So here's my colder region. I don't know. I think dark blue isn't going to come through. Let's do magenta. Ooh. So this is the ground around here. When the temperature around it is cooler than the water will see heat transfer out of it. And so what we see is that water is capable of moderating temperatures at the climate level. Such that areas on coasts compared to areas that are not on the coasts tend to see lower seasonal temperature ranges. Not like lower seasonal temperatures, but the amount of change in temperature over the course of a season or the year is lower. Changes in temperature are in a lower range, right? So if you were to look at the planet, and here's the equator, and you look at, let's say, Africa. I'm going to be bad at knowing exactly where on the equator Africa is. It is gigantic. So here's Africa. And I look at the seasonal temperature variations in different parts of Africa. What I will find is temperatures along the coast here are going to vary much less than temperatures further in on the continent. So we have milder climates, right? And here we'll have extreme temperature shifts. So milder climates on coasts with more extreme temperature shifts on the interior. And that's simply because water's moderating effect on the climate goes down the further away you get from very large bodies of water, right? So that's actually really, really cool. It doesn't mean that everywhere along a coast is mild climate. Obviously, how close you are to the pole matters an awful lot on what your climate is like. It doesn't matter, being on the coast versus being interior when you're really far north. It's just really far south. It's very cold. I don't want to get into the amount of sunlight energy over surface area you're getting, but that has a lot. Got to cool it on my little walkabouts. Okay, so water's temperature moderating is both at the individual level, right? The individual critters, and by critter, I mean like plants and animals. Heck, I mean plants, fungus, animals. And when I want it to mean it, I mean also protists and prokaryotes. Why not? Because critters is a very vague term, but it works on the individual critter level to moderate temperatures, and it works at the global or climatological level. We're going to say A. But now that I've written A, I want to put O. But I don't care enough to look it up. So let's just pretend I knew how to spell it. Here we go. What we're going to do is we're going to put an O here, and then we'll have a weird little thing coming off, and I can claim, oh, that was an A, actually, if it turns out it's spelled with an A. Anyway, water is so effective at moderating global temperature that it's thought that liquid oceans are an extremely important factor for a planet's ability to support life, right? If there are no liquid oceans, then you're going to have global temperature extremes, right? Liquid oceans contribute significantly to temperature moderation. And we're just talking oceans on their own. I'm not even talking about humidity. Humidity operates on the same scale, but humidity is just water droplets in the atmosphere. The thing that gets people here is that they often think of humidity as gaseous water. It's not. It's very, very small particles of liquid water suspended in the atmosphere. So, I don't know. That's just cool to me that it's still liquid water. But because it's suspended in the atmosphere, it's also absorbing atmospheric heat. And when it, gets high enough in the atmosphere and it's cold enough, it'll release heat up there. Or when it rains down, it releases heat. Or, as the air currents drift around into different parts of the planet, it can release or absorb heat. So, humidity itself, water in the air, participates in global temperature moderation. And you can't have an atmosphere with a lot of humidity if you don't have liquid oceans. So, honestly speaking, they're one of the defining important features for having a planet that supports life. Not just in temperature moderation, but we'll get on to ice here in a moment. Fun fact for all you people who are kind of aware of astronomy stuff, when they are searching for planets that can support life, right? They are looking at planets around various types of suns, suns with various sizes, and various heat outputs. And regardless of the type of sun you have, they look for planets that can support life by first looking at how far out it needs to be from the sun to have liquid water, to have temperatures that can sustain permanent liquid oceans. So here, you have steam. It all boils away. And here you have your liquid ocean, far enough away to have liquid ocean. And then here, it all freezes. And you can't have permanent liquid oceans anymore. And so this little range from the sun where you can have liquid oceans is called the Goldilocks zone. This porridge is too hot. This porridge is too cold. This porridge is just right. So it's in different distances depending on the size of the sun and the amount of heat the sun gives off. But that's still the biggest thing when you're searching for planets that might support life, is their presence in the Goldilocks zone. That's pretty cool, I think. And it's all about liquid water, and it's all about these cool facts about water that we're learning, especially water's capability to moderate temperature at an individual critter level and at the global level. We're past specific heat. Water's temperature stays moderate. It allows life. And it's also worth mentioning water's heat of vaporization. So, heat of vaporization is the essentially temperature when a substance changes phase from, since we're talking water, let's just put liquid to gas. Right? So when water changes phase from liquid to gas, water has a relatively high heat of vaporization. High heat of vaporization. If you're familiar, water boils at 100 degrees Celsius, or I believe 212 Fahrenheit for you folks out there raised on the imperialist system. This is the temperature at which water boils. And so when you see water boiling, you've got those big bubbles forming. Those bubbles are forming because those are gaseous water. Those bubbles contain water in its gas form. So that's pretty cool. It doesn't, as soon as it leaves the liquid water, the air around it is not at that temperature, and it starts to cool, which is why it gets steamy and humid around a boiling pot, because it goes from gas back to liquid, but evaporated. So that's kind of fun. But yeah, water has a high heat of vaporization. 100 degrees Celsius, 212 Fahrenheit. You basically don't see this on the planet outside of geothermal systems, right? It's not on the surface. Those conditions are not present on the surface of the planet. And this just means that water stays liquid, whether you're at the equator with the highest temperatures or at the poles with the lowest temperatures. We'll talk about that in a hot second, because water stays liquid at the poles because of good old ice. But yeah, whether you're at the equator where the temperature is hottest, or, even near a lava flow, water is most like, pretend I didn't say near lava flow, because that requires pedantic explanation. But water is liquid, right? Liquid oceans are on the planet, everywhere on the planet. Right? Water will evaporate and produce humidity before it ever turns to a gas. So, maintains those liquid oceans, maintains humidity, maintains that temperature moderating capability, which is very cool, right? So, I said liquid to gas here because we're talking water. Physics-wise, all you physics people, it is possible to have a heat of vaporization where you go solid to gas. that doesn't matter here. So, evaporative cooling, and now we're on to ice. All right, the big thing about water that's really cool is that ice floats. And what we mean by that is solid water floats on liquid water. For all you physics people out there, and, tested thing here, is that this is all about density. Density determines whether or not a solid will sink in a liquid, right? So basically, if you have a solid in a liquid, if it's more dense, it sinks, right? We are going to wholesale ignore the existence of boats because there's something entirely different going on there in physics. So that's not related to this. And this isn't a class on like physics of displacement and whatnot. So if you have a solid in a liquid, if it's more dense than the liquid, it sinks. If your solid is less dense, then it floats. What this means is that solid water, or ice, is less dense than liquid water. And this is very fascinating because density follows a basic trend in the chemical world. And that trend is pretty constant. And it goes like this, right? So you measure density by mass over volume. We don't care specifically about that, but that would be essentially how much mass it has. So grams of mass per, I think it's like cubic meter. So if you trap a substance in this cube and have it filled completely, the amount of mass that takes up is its density, grams per volume. I am going to very quickly change the battery on my camera because my tablet is in tint mode, which flips the webcam upside down, and it's not a very good webcam. So I'm using a different camera for this. So, smoke them if you got them. Probably shouldn't have blanked my screen, but I can barely see that ink. Okay. We should be rocking and rolling. All right. So, getting right back to it. The basic trend of density going from least dense to most dense and going by phases of matter, it goes like this. Gas. When you have a gas, you have relatively few molecules, and they are bouncing all around, moving very quickly. Right? And so gas tends to have a very low density. Gaseous form of water, very low density. Temperature and pressure are going to affect the movement of molecules. The movement of molecules actually determines the phase of matter. We're going to ignore pressure because, this isn't physics. If you want to know the pressure thing, I don't care. Never mind. So, look it up if you want to know it. Wikipedia is available to you. But, in general, decreasing temperature slows movement of molecules. So, when your temperature starts going below the point of being a gas, you transition in general to a liquid phase. Right? A liquid phase, in general, is more dense than a gas phase. And that's just because the molecules aren't moving as fast. And so they tend to be closer together. And weirdly enough, how close together the molecules are determines the density and basically determines the phase of matter. So these molecules are moving much slower, and because of that, they tend to be much closer together. So, water follows this. Gas is the least dense phase. Liquid is the next phase. For most substances, when you get to a solid phase, right, molecular movement basically goes down to vibration. You can watch this happen with candle wax, right? You light a candle and wax melts and it drips down the side of the candle. And as it drips down the side of the candle, it gets further away from the heat source and the molecules start moving slower. And at a certain point, they stop moving except for little bits of vibration, and the wax solidifies in the shape it was in. So that's pretty cool. For most substances, when you have a solid, they are packed together right? Let's just put a couple of wee lines for vibrations. Anyway, they're packed together, and there's very, 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 very little space between the molecules. Very little space. Betwixt the molecules. So another way of thinking about this density thing is the amount of space between the molecules, right? More space betwixt the molecules equals less dense. And again, that makes sense because density always takes into account volume. If you're trapped in a cube, and your molecules have a lot of space between them, versus molecules that have less space between them. The molecules are what actually have the mass. So, more molecules, more mass. Right? So here I've got 1, 2, 3, 4, 5, 6, 7, 8, and let's keep with 3 dimensions. Right? So 10 molecules in here. I don't know, I've messed that up. Anyway, I've got like 10 molecules in this cube, and then I've got way more than 10 molecules in this cube. Right? So the molecules are what are contributing the mass. So more space between the molecules means you have less molecules in there, which means it's less dense. And you can see I showed this with my liquids, right? You can think of it this way, and you can think of it with temperature decreasing movement, so they're closer together, and since they're not pinging all over the place, they don't move as fast. So if you were to like quickly put a box around it, you'd catch more. Think of it like you're trying to capture them in a box. You're real sneaky. You have a box trap and you drop it on them, right? You drop your box trap on a gas, there's very few in there. You drop your box trap on a liquid, you catch more because they're moving slower. And when you throw your box trap on a solid, you catch a ton, right? More space, less dense. I think I've gone about this as much as possible, but this is the general rule in physics, is going from least to most dense. Gas is the least dense, liquid is in the middle, solids are the most dense. And that makes it particularly curious because, once more, in water, the solid is less dense than the liquid. I'm getting that phone thing where it just turns off the menu the moment I hover over it. No. All right. I have managed to accidentally stop my presentation. So I'll be Stitch incoming. Alright, let me tell you about that dude who was talking about density, right? He's just crazy. There, that was my Stitch incoming. Pretty sweet, right? I think I was supposed to like either crap on the person or say they were exactly right. But either way, I successfully stitched, young people. So expect your personal information to be stolen by China now. I think that's what Stitch incoming means. So we were talking about ice and how ice is less dense than water. And that makes it particularly weird because ice is the solid and water is colloquially the term for the liquid. Although, technically solid water and liquid water are the terms I'd use for this. Ice is still water. So, when it's hot, sometimes I put some water in my mostly water solution in order to cool it down. That's how iced coffee works. Anyway, ice is solid It's it's less dense than the liquid, and that's weird. Knowing what we know now about density, we can now talk about why ice is less dense than liquid water. And that goes all the way back to that thing that I said gives water all its special properties. And that is the electronegative oxygen allowing hydrogen bonds between the hydrogen in water molecules and the oxygen in neighboring water molecules. Yes, right back to hydrogen bonds. Hydrogen bonds are what gives it its high specific heat. Hydrogen bonds are what gives it its high surface tension. Hydrogen bonds give it that capillary action and adhesion thing. Hydrogen bonds give it the high heat of vaporization. Hydrogen bonds are why ice is less dense than water. So let's talk about how hydrogen bonds and water molecules interact as molecular movement slows down. And for that, I need to talk about the fundamental laziness of the universe, right? So when you are looking at something like molecular movement, gases are moving very fast, and they're bouncing around in my container. They're very far apart precisely because they're moving really fast. And this is the lazy way gases pack together, right? In other words, you're not going to be tested on this concept, but it's helpful in understanding why water molecules do what they do when they cool down from liquid to solid. And the basic concept is this. The least energy configuration. The laziest configuration. Basically, with molecular movement, as molecules slow down, their distance from each other gets governed by the amount of energy in the system that it takes to move them around. Gases, they move around real fast. It doesn't take a lot of energy to move a gaseous phase around, so they're real spread apart and they move real fast, right? I guess the velocity is based on it doesn't take much energy to move them around, but here nor there, right? They're bouncing around and moving very fast because it doesn't take much energy. In fact, if you wanted to get gas molecules to stay close together without meaningfully changing the physical conditions that allow them to be a gas molecule, generally you need to add a bunch of energy to the system, right? The most common way to do that is pressure. So, under pressure. So if I was able to put a bunch of pressure on this and introduce the energy associated with what's required to hold that pressure, I could slow those gas molecules down. But again, that takes energy. And the universal law of everything is you're moving towards laziness, right? So if it takes a bunch of extra energy to get it into that position, then it's not going to happen, right? As temperature goes down, because that's what we were talking about, governing phases of matter. I just mentioned pressure, but again, we're ignoring it in favor of temperature. right? Heat energy goes down. So we're still talking about the amount of energy in the system. If it's in its gas phase, that means there's more energy from heat. So they're able to bounce around, move fast, bounce around. As our temperature goes down, there's less heat energy in the system. And so the molecules slow down. And at this point, the lazier way the molecules end up positioned is moving around slowly. Their velocity goes down precisely because it's lazy. They're still spread out because they're moving around, and because pushing molecules together takes extra energy when they're at a when they're at conditions where they can be liquid and move around, right? They're still capable of moving around with the energy in this system, so holding them close together is unnatural. Again, to get them real close together, you'd probably need to apply energy in the form of pressure. You'd pressurize the system to force them together. And again, that's adding a bunch of energy to it. And that's why when the energy in the system is slow enough that they transition to a solid, right, the lazy configuration of a solid is close together, because there's no energy causing them to move apart, right? We're just down to enough energy that the molecules vibrate a little bit. So now these molecules that are close together stay together because there's not enough energy to break them apart away from each other, so they pack together, right? We're moving towards the laziest configuration. If I wanted these molecules to move apart from each other, I would have to add energy. So heat or physical force. That's not to say all the molecules in like a solution would immediately glue together, but that's to say that, like, you know, if I had my solution and I had some gunk in there and the temperature dropped to the point where they'd solidify, I'd get the ones nearby each other slowing down enough that they turn to solid gunk. They wouldn't all immediately like magnetize together like buckyballs. They'd just solidify, right? So it's the laziest configuration. Hydrogen bonds affect the laziest configuration. That's kind of a big deal. So when you look at the lazy configuration for liquid water, the molecules end up closer together because they're still moving around, right? Occasionally they get close enough to hydrogen bond, but then they'll move along. And as they move around, they'll hydrogen bond to a new neighbor. Right? These molecules are just moving around. As you slow them down and they get closer together, instead of packing together without going too deep into it, the laziest configuration results in them being more spread out than they are as a liquid. If it helps, think of it like the hydrogen bonds pushing them apart. Right? So as they slow down, they get close to each other, and instead of packing together, think of it as if the hydrogen bonds push them apart. It's not truly what's happening at the, physics of chemical bonding and temperature and solidification level, but it's probably the easiest way of thinking as far as why they're spread out more than liquids. As they slow down, the hydrogen bonds push them apart so that the laziest configuration is more spread out than the liquid phase. Right? So the liquids are closer together at maximum laziness. The hydrogen bonds keep the solids further apart than the liquids at maximum laziness. What this results in is that as they slow down, and the water molecules are pushed apart, we get this organized area of empty space. I'm doing a cube because I'm lazy and that's easy, but we have this empty space because they're pushing each other apart in lazy configuration in 3 dimensions. So what we have is a crystalline structure with lots of empty space. And so, if I were to grab a cube and trap ice in it, because they've pushed each other out like that, and there's a bunch of empty space in there, I would get fewer water molecules, fewer H2O in there, in the form of ice than I could with liquid water. Don't rub up against the tripod. Jess. Okay. Not too bad. Okay, so we have established why ice floats. The number of hydrogen bonds arranged into the crystalline structure doesn't actually matter. I was just trying to say that for this 3-dimensional lattice picture. So that's like a physically accurate picture of the crystalline structure solid water forms. And on the right is liquid water being much closer together. So that's why ice floats. But this is all about why water's chemistry is so important to life. And that begs the question, why is floating ice important for life on Earth? Why is floating ice important for life on Earth? And this requires us to simply talk about the way that ice forms, just when you're looking at a body of water. So here's my ground. Here's the surface of my water. And if ice is going to form, that means the air temperature is going down. The air gets colder, right? What governs how cold it is the atmospheric temperature. You go burr when the air is cold, right? So it's the air that gets cold enough that causes water to freeze. So the air interface is where we're going to see water freezing, right? So again, this isn't a sentence that's going to be tested on. I'm not going to put the air-water interface in there. So, but H2O freezes at the air-water interface. This is just me going in depth on explanations, right? The further away from the air you are, the less effectively the air cools you, right? So essentially, if we're looking at the ground, underneath the ground, far away from the air, is going to be warmer than the part of the ground that's closer to the atmosphere and directly exposed to the air. And the ground heats more slowly, the ground cools more slowly than the air, right? In other words, the ground has a higher specific heat than the atmosphere. How's that? Heat transfer is slower from the ground. Anyway, that's why when it first starts snowing and the air is cold enough for snow to happen and the snow hits the ground, the snow melts. Because it takes time for the ground to cool enough, right, that snow can stick to it. Same holds true for our water. Right here at the air-water interface, water is going to be colder than below the air-water interface. The further down into the water you get, the warmer it is. It may not be like wear a bathing suit warm, but the further away from the atmosphere you get, the warmer it is. So ice is going to form at the air-water interface. I explained that probably too thoroughly, but I just want to make sure everybody knows. So, when it gets cold enough for my water to freeze, the ice at the surface forms and we get our ice. And now what we have, because it floats, is a layer of ice, right? And here, now we have our freezing temperatures because it's in contact with the atmosphere. Here's our freezing air temperature. But below the ice, it's warmer than the air. Right? Ice is going to get as thick as the temperature can transfer through. But at a certain point, the ice is so thick that the cold from the air can't cause the ice to stay freezing temperature all the way through to the bottom, right? As long as, so when you're thinking about the ice, right, it forms as that thin layer at the surface. And as long as the the temperature of the air, can transfer effectively through that ice, the ice will get thicker, right? And as long as the temperature is transferring effectively through the ice gets thicker. But at a certain point, temperature is no longer able to effectively transfer all the way through the ice. So if this is my freezing temperature and the ice is cooling, at a certain point, it can't cool any further, right? Essentially, the specific heat of water means the energy associated with freezing just can't make it through. Not enough temperature transfer to freeze the water. This is why the colder it is, the thicker the ice on a lake, right? But if the lake is deep enough, it won't freeze solid. So this is me going in depth on it, but if you want the lazy glossing over explanation, which is really as far as we need to go, as far as a test would go, because the water beneath is protected from the freezing air above, the water beneath is warmer, right? So the water under the ice is warmer than the air. Fancy term for that is that ice insulates the water beneath it. And because of this, even at the poles or even in freshwater lakes, you don't have the entire water body freezing solid, right? Even when the air temperature is cold enough to freeze, the water beneath stays liquid, right? So we can keep liquid water. And because of that, critters can survive. If you have a koi pond, oftentimes what you'll do if you want to keep koi all year round is have your pond roughly 6 feet deep. I think that's for Colorado temperature variation. If your pond is roughly 6 feet deep, then it can't freeze solid. Regardless of what temperature the air here in Colorado gets to, there will constantly be liquid water in the bottom of your pond. So if you have a 6 foot deep pond, those koi can just chill at the bottom in liquid water. Chill. Anyway, they can chill at the bottom in that liquid water and overwinter. Their body reactions slow way down, so they don't need to eat as much, and they just lazily survive, right? As long as their heart rate goes down, as long as all the reactions in their body slow down, they don't need much oxygen, and they just sit there and like their fins twitch every so often to keep them in one spot, and they just survive the winter. And that's how critters can, aquatic critters can survive lethal temperatures, right? There's fun other species specific mechanisms to survive lethal temperatures, but when you get down to like basics, critters that don't have specialized adaptations to surviving temperatures, and critters that can have their body reactions slow way down without dying, and not mammals, then ice's insulating effect is plenty for them to survive. And that's why life on Earth can survive even when the temperatures are hostile, even where the temperatures are hostile to life on Earth. When you go up to the poles, if you're a mammal and you like try and walk around in the air temperatures up there, you're going to die real fast because, you know, if your body core gets cold enough, like the homeostasis stops and you die. That's just mammal stuff. But if you're certain types of cold-blooded critters, the air temperature might kill you. But the water temperature beneath the polar ice, you can survive in. Pretty cool. So that begs the question, what if ice didn't float, right? What if ice followed the rules of matter and the solid was more dense than the liquid and sunk? All right, well, when the air temperature got freezing, ice would form, and then it would sink to the bottom. And unfortunately, when ice sunk, there would be liquid water exposed to the air temperature that's cool enough to freeze it. And so it freezes, and then it sinks. Right? And then, because it sank, you know, there's water exposed. You might, if you're particularly perceptive, see where I'm going. Suddenly, water levels are increasing because ice is, you know, at the bottom, displacing the water. And so water's starting to cover the land, and it's still freezing. And then eventually, the whole bodies of water, like all the oceans, freeze solid, and the oceans have been pushed up and cover most of the continents, and the continents covered in frozen solid water, and you have nothing but an ice ball for a planet, right? Ice ball planet, and everything done died. So, once more, liquid water is required for maintaining life on a planet. You know, when you get too far away from the Goldilocks zone, you get a frozen ice ball in and of itself. But as long as you're in that Goldilocks zone, even if temperatures are cold enough that things are frozen most of the, like things are at freezing temperatures most of the year, you're still going to have liquid water under the ice, and you're still going to have places where life could thrive, right? The first life on Earth was aquatic. Life on Earth stayed aquatic for a very long time. So you could, you know, your single cells could survive underneath a planet that was covered in ice, but as long as it's in like the Goldilocks zone, that ice isn't cold, like the temperature isn't so low that the oceans freeze solid. So the ice insulates the liquid water beneath, and life can find a way. Anyway, insulate, by the way, keyword. Okay, continuing on. Erosion, a fun concept here, is that erosion is actually something that ice helps along and is also good for life. right? So erosion is going to be something that we're talking about when we're talking about earth and rocks, right? So say here you are, here's a mountain, like, there we go, big hunk of rock. Maybe here's the Rocky Mountains, right? The Rocky Mountains, a long time ago, due to some tectonic geological event, erupted out of the ground. So the Rockies were not always a mountain range. You can actually see evidence of this if you go to like Red Rocks Park, because all those layers of ground. This is, you're not about to get tested on this geology, but in general, when you look at the layers of Earth, the layers near the top are the youngest, and the further down you go, the older you get, right? And the Rockies were originally this deep layer. But then a tectonic event happened, and the Rockies were launched upwards through the layers beneath it. And what happens is, if you go to some of the parks at the foothills on the east and west of the Rockies, you're going to see slanted rock formations. The height is changing just to illustrate this. But that's just because, you have this layer of rock, and then the Rockies punch up through it. And so the layers turned up, and when you go up to Red Rocks Park, you're going to have these angled rock formations. And the ones closest to the mountains are going to be the oldest. And it's actually very cool. If you go to Red Rocks, I highly recommend you talk to like the volunteers or a guide or something, because they can tell you what the layers were formed from. So I think this middle layer was actually formed from the beaches of an inland sea. And if you go up to like the little tops of these little outcroppings here, they've eroded, and it's actually beach sand, which is pretty cool. Apologies for that aside, but I say that because when the Rockies first formed, they were that deep rock layer, and they were solid rock, right? There's no oceans crashing against them. And at the tallest part of the Rockies, there's no like streams, there's no moving water to grind away. And so how do these, rocks get smaller and smaller? Because big rock becoming small rock is important for plant diversity and then animal diversity. Because if you have a big hunk of solid rock, right, there's not a lot of things that can live on that solid rock. You can get like some lichen stuck to it. And also there's like a few species of really sad pine trees that look like they're about to like die and fall over, because they've evolved to grow scraggly, twisted stems, because the wind is so rough up at the top where it's all solid rock. Anyway, not a lot of plant life, which means not a lot of animals that eat that plant life, which means pretty much low biodiversity. But here in Colorado, there's a lot of seasonal temperature variation. And no rock is completely solid, right? Especially with how violently they punched through the layers beneath. And so they'll have little cracks in them. And as long as there's little cracks in the rock, when it rains or when it first starts snowing and the ground isn't cold enough for it to stick, the snow melts and invades the cracks and fills the cracks up with liquid water. But then it gets cold enough that the water in the cracks freezes. And if you've ever stuck a can of soda or a bottle of water that's completely full into the freezer, you will have had first-hand experience with the fact that solid water is, less dense than liquid water. That extra space in there expands and your cans of Coke explode. But what happens here is once it expands, the chunks of rock get liberated. I want this. Okay. Maybe this. Whatever. The chunks of rock get liberated. And they fall down. And you get smaller rock. Small rock forms these, rock slides. And these big piles of smaller rock have more space for plants. And so there's more plants growing in here. Maybe there's a few trees that can grow and have their roots in the, cracks and in the depths of our rock pile. And with more plants, there's more animals that can eat those plants. And then there's more animals that can eat those animals. Circle of life. And then, smaller rock becomes smaller rock. And more plants. Until eventually, small rock become very, very small rock. And you have my absolutely non-scientific term, dirt. Lots of things can have their roots move all through the dirt, right? Dirt is great. And then as things die in the dirt and decompose in the dirt, you have a bunch of organic matter in there. And dirt plus organic matter is soil. So, what's really cool is, by the way, big rock go to small rock is erosion. Big rock, smallest rock. This is erosion. Ice is a very important mechanism for erosion in areas that don't have like an active body of water wearing away at the ground around it or waves crashing up against it. Ice becomes a really important source of erosion, which is very cool. So ice's capability to crack rocks apart and make big rock, small rock, very important for increasing the plant communities, right? Soil supports the most diverse plant communities, so soil supports the most diverse animal communities. So again, yet another way that water, that ice specifically increases life's ability to thrive, right? So, very cool. Solid water being less dense and expanding improves erosion. So that's very cool. For those of you who lived through like the early 90s, there were, so many cartoons that talked about how erosion was bad, and PSAs about the environment that talked about how erosion was bad. Human-caused erosion is bad, but natural sources of erosion are just natural progression of the planet, and ice is an important source of erosion. So, very cool. Big rock go to small rock, plants more, animals more. Yay, ice. All right, now we're on to the final part of the lecture, and this is all about water's capabilities as a solvent. So first off, let's get as basic as possible and talk about what a solvent is in chemistry. And solvents are part of the chemistry of mixtures, right? So, in chemistry, we have the term solution. A solution is a mixture of two components. A solvent and a solute. A solvent is the thing that, let's just talk about dissolving. So a solvent is the thing that does the dissolving. And a solute is the thing that's dissolved. Right? The physical properties of a liquid determine the diversity of things that can dissolve in it, right? Essentially, how many things that are, I don't know what the right word is, but attracted to or have an affinity for the molecules of your liquid determine how effective of a solute it is, right? Liquid water can hydrogen bond to anything polar. I'm going to switch off orange here because it's not so visible. Go back to this blue. So liquid water, because in solution chemistry, we're almost always talking about a liquid solvent. There's different terms when you have a mixture that's like solids. Anyway, liquid water can hydrogen bond to anything polar or with polar regions, like things that are partially polar. And in the context of solution chemistry, what happens when something polar ends up in a mixture with water is pretty cool. And we're going to demonstrate it with something fundamentally and always polar, good old sodium chloride, right? Ionic bonds are fundamentally polar. So ionic compounds dissolve readily and very effectively. Because again, remember, an ionic bond is all about stealing electrons. Chlorine steals an electron from sodium, and now that it has one extra electron, it has a negative charge. Sodium has lost an electron, And so with one less electron, it has a positive charge. And I dropped a thing and it clicked a button and my blank screen went away. Sodium positive charge, chlorine negative charge. So fundamentally, ionic compounds are polar. That's just fundamental to an ionic compound, and they have very strong polarity. Like, it's just two things, a cation and an anion. So if you have an ionic compound, a compound formed from an ionic bond, it will super easily dissolve in water. At the chemical level, what happens is, you have your water, and you have your sodium chloride, and it gets in the water, and it encounters the polarity of the water molecule. Wherein hydrogen has that partial positive charge and oxygen has that partial negative charge. Sodium, being positively charged, gets yanked off of the chlorine and ends up hanging around the oxygen because opposite charges attract. Chlorine, being negatively charged, also experiences that yank apart force and hangs out at the hydrogen pole. This is not fundamentally destroying sodium chloride. That's worth noting, right? Sodium chloride is not destroyed in this. So this isn't a chemical reaction, right? For two reasons. One, water is not altered, right? We don't have like sodium chloride plus water and reactants over here, and both of them get broken, and you end up with, I don't know, OCl plus H2Na, right? This is not a thing happening. Water stays water, but the sodium chloride ions are separated. They're pulled apart. So it's not a chemical reaction. When something polar gets in water and the polar region gets pulled apart, there's a word for it. Dissociation. So sodium chloride in water, our solvent, dissociates and we get our sodium cation and our chlorine anion, and they're, held apart because we've got electronegative oxygen having a partial negative charge, and the hydrogen with its, general lack of its electron having a positive charge. So the charges of the sodium and chlorine have them attracted to different areas of the water molecule, and so they end up being separated, right? So they're not hydrogen bonding. This is a force of attraction based on charge, not electronegativity. So, if I were to if I were to attempt to quickly draw how these might be hanging out in water, when water is hydrogen bonded together, right? There we go. Right, it would probably look like this. Sodium over here, chlorine over here. Right? They're not disrupting hydrogen bonds or anything. They're just yanked apart and just sort of attracted to different parts of the water molecule. So they're separated. Right? Polar regions are separated, and the cation hangs out with the oxygen, and the anion hangs out with the hydrogen, right? Because of our polarity. So, dissociation is very important. The capability of water to dissociate things is what makes it a good solvent. Water's charges are what cause polar things, or things with polar regions, to separate apart and dissolve in water. The more polar regions, or the more fundamentally polar it is, the more quickly it dissolves. So think about like dissolving salt in water versus dissolving the same amount of flour in water, like wheat gluten or something like that, or wheat. Let's just say wheat flour, right? Wheat flour consists of like carbohydrates and gluten, and those are very large molecules. So they've got like polar regions rather than being like very fundamentally polar. So when salt hits water, like it rapidly disappears and dissolves very easily. When flour hits water, you have to do a bunch of stirring in order to get it to dissolve. And that's just because it takes time for flour to dissociate. Those, sodium chloride, very small, very fundamentally polar, dissociates very easily, very quickly. Carbohydrates and protein and flour, right? They're going to take more time to be separated apart and to dissolve. So it's all about water's polarity, being able to separate the polar regions on solutes. So water, getting back to it, is amazing as a solvent because it can hydrogen bond to anything polar or with polar regions and dissociate it. This is what makes water a fantastic solvent. Water is generally referred to shorthand as a universal solvent. Water is not truly a universal solvent, right? Water has to dissociate a chemical to dissolve it, and only polar things or things with polar regions can be dissociated. So this is why when we talk about water's ability as a solvent, what we're going to talk about is hydrophilic, hydrophobic, once more. Hydrophobic things don't dissolve in water. So hydrophilic, soluble, they dissolve in water. They're good solutes. Hydrophobic things, insoluble in water. They don't dissolve. What it comes down to is hydrophilic things are polar, or they have polar regions. And so they dissociate in water very easily. Hydrophobic things are fundamentally non-polar. And so they cannot dissociate in water, right? So sometimes the dissociation is as easy as hydrogen bonds forming in order to yank apart the negative region. Sometimes the molecule is so small that it just gets yanked apart. Like with something big, like a chunk of carbohydrate from flour, that positive region is probably going to have some hydrogen bonding going on as well, and then the negative cation is likely the negative cation. The anion, the negative ion, is likely to still be kind of big, like relative to chlorine. And so it'll probably be big enough that we have some hydrogen bonding going on. And then the cation will just be attracted to chlorine. If there's hydrogen in it, if there's a bunch of hydrogen on this thing, you might get some hydrogen bonding there. But regardless, what it fundamentally comes down to is whether or not there's polar regions and it can dissociate. So, hydrophilic things, polar or polar regions, dissociate in water. Hydrophobic things, non-polar, don't dissociate in water. They are not solutes. So water is not a universal solvent, but there are way more hydrophilic things than there are hydrophobic things. Hydrophilic things are significantly more common than hydrophobic things when it comes to solutes. So water gets shorthand called a universal solvent because if you have some kind of powder, you can probably dissolve it in water. All right. So solution, blah, 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 blah. Okay. Water as a solvent, not just ionic compound, anything slightly polar, blah, blah, blah. Vocab, hydrophilic, blah, 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 blah. One quick note about hydrophobic stuff that I always like to emphasize is that hydrophobic things are not pushing water away. Water is pushing hydrophobic things away. So if I have this hydrophobic thing and I have a bunch of water molecules around here, they're going to want a hydrogen bond with each other. They're going to want to form their little water molecule clique. And so what happens is this thing gets knocked around and knocked out of the way as they form their little hydrogen bond clique. And your poor hydrophobic thing gets pushed away from these water molecules, getting together to discuss, water molecule stuff like, oh, did you see chlorine? Oh, it totally just ditched sodium in the water. It's so slutty. Jeez, I could never. And then the oxygen's like, you know what? I would. Because I'm electronegative, but chlorine doesn't like me. I don't know. Whatever. And the nonpolar stuff gets pushed away. And that's why it fundamentally doesn't mix. That's why you get a layer. So oil is the most famous. Oil tends to be less dense than water. And so you get a layer of oil on top of water. And that's just because the water hydrogen bonded together and pushed the oil away. So water repels hydrophobic stuff. It's not the hydrophobic stuff choice not to hang out in the mixture. It's water repelling it. Jeez. All right. As is the case with digital cameras, they eat batteries. So, time to swap out the battery. Another break. Woo! All right. So now that we have established the concept of dissociation and water being an extremely effective solvent, let's talk about acid-base chemistry. Acid-base chemistry is really important to the biological world and just fundamentally important in the chemistry of the universe. But when we get down to it, acids have special properties, bases have special properties. When you say something is an acid, you are saying that it has the properties of an acid. When you say something is a base, you are saying it has the properties of a base. Mostly what you'd think of is that something very acidic or something very basic can burn your skin. So, you know, that's what you think of shorthand, but there's a lot more properties of acids and bases than just like whether or not it's going to burn your skin. However, this is not a chemistry class, so we're not going to really talk about the special properties of acids and bases. However, we will talk about acid-base chemistry in general and measuring the strength of acids and bases. And to do that, we need to know chemically what makes something an acid. So why do we call some things an acid? Why do we call some things a base? So when we look at a solution in acid-base chemistry, there are three fundamental categories that you could give it. One, it could be acidic, right? It has acid properties. Two, it could be basic, or, important word, alkaline. For our purposes, we're going to use them interchangeably. A basic or alkaline solution has the properties of a base. The last category is a solution that has neither acidic properties nor alkaline properties, right? Neither acidic nor basic properties. When an acid and a base get on Facebook and start arguing with each other, this third party says, whoa, 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 don't involve me. I'm neutral. So, hey, mentioning Facebook, that's right. I'm over 40. Anyway. Whoop. This is the three ways you can shake out. And what makes a solution acidic, neutral, or basic is just how many of a thing is dissolved in it. How many of one specific thing is dissolved in it. And that specific thing is protons. So, when talking about how many of a thing is dissolved in something, we are referring to the concentration. Right? Concentration, when you come down to it, is like volume of X per every volume of Y when your X is a liquid. So like, or number of X. So here we're just saying protons. So let's just say number of protons per milliliter of water. Right? So this right here is the concentration. If you have 100 protons per milliliter of water, then in 1 milliliter of water, you'd have 100 protons. In 2 milliliters of water, you'd have 200 protons. So that's just the concept of concentration. So when I say the number of protons dissolved in a thing determines whether it's acid, basic, or neutral, what I mean is that the proton concentration determines the acid-base chemistry, right? Acidic, neutral, or basic is fundamental to every single solution there is, right? Because there's no situation in which you have a solution where there are literally no protons in it. You can't have a solution that doesn't have dissolved protons. That doesn't happen in chemistry. So everything is going to be acidic, basic, or neutral. So that's important to note because, acid-base chemistry is kind of a universal thing. And let's talk about what makes something acidic. All right. So, what is an acid? When we say an acidic chemical, I'm going to move my mouse. I keep bumping it. When we say an acidic chemical, or a chemical is an acid, what does that mean? Right? So, I'm going to get ever so slightly pedantic here. Chemicals are either like intrinsically acidic or basic, or they are chemicals that could, in solution, act as an acid or base. Because the only thing you need to do to be considered an acid is to increase proton concentration. So an acid is any chemical that increases proton concentration. That's all you have to be an acid. If it is put in a solution and proton concentration goes up, it's an acid or it's acting as an acid. I include that act as an acid or base because when you get into organic chemistry, things get weird. And then you have chemicals that are not an acid, but in certain mixtures they act as an acid. Like in certain conditions they can kick off a proton, and that's acting as an acid because they kicked off a proton, which means proton concentration went up by 1 proton per milliliter, let's say. So that's just me being pedantic. Act as an acid or base, because the universe is not so simple as to be that everything is either intrinsically acidic, basic, or neutral. Organic chemistry gets weird and complicated, and while I do love it, when biology gets weird, complicated, and messy, I despised it when chemistry got weird, complicated, and messy. So, but that doesn't stop me from being a pedant. So there you go. A pedant? I don't know, man. I probably, yeah, never mind. Anyway, technically correct is the best kind of correct. Any chemical that increases proton concentration. So first off, proton concentration is a lot of things to write over and over and over again. And I am way too lazy to write those over and over and over again. So allow me to introduce you to my abbreviations for proton and for concentration. First off, in chemistry, when you have something in brackets, what that means is you're talking about the concentration of a solute. So that's very easy. So if I have, NaCl in brackets, then you know this is NaCl dissolved in something. Very easy. So that's concentration. The concentration of a thing in the solute. Throw brackets around it. Now let's talk about abbreviating proton. So ultimately, if I say proton, I am referring specifically to, who could have guessed it, the subatomic particle named a proton. Oh, geez, complicated stuff here. So, a proton, right? When we, talked about chemistry, we talked about protons, electrons, and neutrons. So, right, that was ye old pictures from chemistry. And to throw it back, the number of protons equals the specific element. Right? If you have 6 protons, you have carbon. That's all you need. It does not matter the number of neutrons or electrons. 6 protons means carbon. So over here, I have the word proton singular. And that means that 1 proton is hydrogen. But I'm just saying proton. H here on its own means hydrogen from the periodic table. H, 1, atomic number 1, and like 1 point something 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 in as far as atomic mass goes. So number of neutrons, 0. Atomic mass minus protons is number of neutrons. 1 minus 1, 0. So the nucleus of my hydrogen is a proton, and if it's on the periodic table, the number of protons is also the number of electrons. But I want to refer to a singular solitary proton. What would I have to do here to get a single solitary proton? That's right. I'd have to ditch the electron. Without my electron, what's my total charge? That's right. Positive. I have a +1 charge when I have a singular proton. And that means when abbreviating proton, it is a positively charged hydrogen. So proton is H+. It's that easy. So if I have brackets and H+, what I mean is proton concentration. Not so bad. Way less time to write than the words. So, an acid is any chemical that increases proton concentration. You can also think of it like it donates protons to the solution. This is pretty easy to illustrate with ye old hydrochloric acid. Hydrochloric acid is a go-to example of a chemical that is intrinsically an acid. No matter what situation you're in, you put hydrochloric acid in something, proton concentration is going up. And that's because hydrochloric acid in solution dissociates. And of course, this is the water lecture, so in solution with water. All right. So hydrochloric acid first. Hydrochloric acid, amazingly enough, hydro means we've got a hydrogen, chlor means we've got a chlorine. This is hydrochloric acid, HCl. Right? In solution, your HCl dissociates into a proton and a chlorine anion. This makes hydrochloric acid intrinsically acidic because in solution it separates out and you definitely get a proton. So one HCl gets you +1 proton to your solution. It increases proton concentration. All it has to do is kick off a proton, and you've got an acid situation, right? If it can fundamentally kick off a proton, then congratulations, it's acidic. So HCl in solution dissociates into a proton and a chlorine. So it increases proton concentration, so it's an acid. It's part of a class called strong acids. Basically what that means is that in solution, this proton isn't going to bind back up to that chlorine. So in other words, it's not two ways, right? When you have a reaction that can go back and forth in chemistry, you do like a little back and forth arrow. So if this was a back and forth arrow where the proton could move around and knock into the chlorine and then easily bind back up into HCl, it'd look like this, and that would be generally referred to as a weak acid. But this, because of the chemistry of water, is a one-way reaction. It's a one-way trip. It dissociates, and the proton hangs out by the oxygen, and it stays a singular proton. It just hangs out there and be a proton the whole time. So it's a strong acid. Well, this is fundamentally, this is it. That's it. You want to know what an acid is? It increases proton concentration in solutions. Ta-da! Lots of things are acids. Water in the right situation can act like an acid, right? So the right situation, if you have a solution of water, two water molecules, essentially in certain situations could, let's just say, bonk into each other and break apart. And you could end up with H3O, positively charged, plus OH, negatively charged. This is hydronium. This is a hydroxyl. Hydronium is a weird one. When you look at oxygen and you talk about its valence, right? This is oxygen showing the fact that it has 6 electrons in its valence. 2 are paired, 2 are unpaired. And so hydrogen comes along and you get 1 there and 1 there, and now you have H2O. But if you've had these water molecules knock around into each other and a proton gets knocked loose, fundamentally, a singular solitary proton can still get a satisfied valence. It has an empty valence, but it still has a number of electrons necessary to have a full valence. And if you have a single solitary proton, how many electrons will it need to have a full valence? That's right, 2, because it's the innermost shell. And what do you know? We have 2 electrons right here. And because of the weird angle of water, sticking those hydrogens down below, these 2 right here, technically they're available. And so my proton could hang out there. And remember that proton is H+. So it says, whoa, water, you've got that little unpaired, or you got those 2 electrons just sitting right there in the open. Don't mind if I do. And that's how you can get hydronium, despite the fact that water is non-reactive because all its valences are filled. Hydronium, as you might imagine, is not stable. Hydronium is not at all stable. It is very easy for the proton hanging out on hydronium to get knocked loose. And when it gets knocked loose, you get water, because the proton just got knocked loose, and a proton. And the reason water is a very weak acid, when water acts as an acid. Water itself, just H2O pure, is not acidic nor basic. But if water molecules get knocked around and you can get hydronium, hydronium then acts as an acid. So water can, in the right situation, act like a very weak acid, because a chemical reaction can occur and you get hydronium. Anyway, it's very weak, not because the hydronium to water and a proton is reversible or anything, but because of what you got left behind when you first had those two water molecules knock into each other. And that's ye old hydroxyl over here, OH minus. And here's a protein, H plus. What do you know? We've got 1, 2 hydrogens, or H2. And looky here, an oxygen. So H plus plus OH minus gets you right back to H2O. So water can act like an extremely weak acid because basically you get hydronium, it's unstable, and it knocks its proton off, and then that immediately binds with a hydroxyl, and you're right back to H2O. So it's a peculiarity of water that under the right conditions, hydronium can form from two water molecules. So, kind of cool. That and in solution itself, there's always protons. So, there's always protons. There's no such thing as a solution with 0 protons. So, it's certainly possible for one of the loose protons to just attach and make hydronium on its own. There's not a lot of protons in pure water, but they're still loose protons. So you can also just get H plus H2O, getting you hydronium. And then hydronium is unstable, and you just go back to H2O, and that dissolved proton just continues to hang out in the system. Yeah. Water is a weirdo. If we're talking acid-base chemistry, try not to use hydronium. Talk about hydrochloric acid, man. It was so much less complicated. But water is peculiar. All right. So, an acid increases proton concentration. That's all it needs to do. Right? Hydrochloric acid is cool because you can find it in your own body, serving an important biological function. And what is that function? That's right. It's in stomach acid. The acid that makes up the acid part of stomach acid is hydrochloric acid. So, stomach acid is certainly a great term if you're not a scientist, gastric acid would be the scientifically correct term. So, gastric acid, the acid part of it is HCl, hydrochloric acid. Very weak, but strong enough still that the part of your stomach that comes into contact with HCl is not the direct tissue of the stomach, right? The stomach tissue produces gastric acid and has muscle associated with it and stuff like that. But when gastric acid is poured out into the stomach, there's a whole lot of mucus layers. A whole lot of mucus layers, because gastric acid is strong enough to burn the normal tissue layers of the stomach. That mucus exists there to just be damaged by the gastric acid instead of your own tissue. The reason gastric reflux sucks and feels like burning, heartburn, is because it makes it a little ways out of the stomach and into your esophagus, and your esophagus does not have nearly the levels of mucus protection as your stomach, so that's acid right against your esophagus, and you're literally feeling tissue being damaged. So, all right. Increases proton concentration. Great example in the body is gastric acid. This is, let me erase all this. This is like stuff that you're not going to get tested over, but for my math-brained people who might like this sort of stuff, when we talk about proton concentration, I hid ink markup. That's not going to work. What I need to do is this button that erases. So when we talk proton concentration, we talk about molarity. Molarity is moles per liter. Mole is a very general term used for the chemistry of very, very, very little things. I mean, technically a mole could be anything. A mole is just shorthand for a scientific notation for a very, very large number. 1 mole is 6.022 times 10 to the 23rd particles of something. So, 6.022 times 10 to the 23rd. If you are not a math-brained person, ignore all of this. Right? You're not going to get tested on molarity, its unit, and molarity conversions or anything. But, so, when we talk about proton concentration, it's moles per liter of water. So, moles of protons in 1 liter of water. Right? Because this is the chemistry of water. So, in 1 liter of water, you'd have 6.022 times 10 to the 23rd protons. When we talk about measuring the strength of acids and bases, we'll use scientific notation. If you have 1.0 times 10 to the negative second, or 0.02 molar, that means you could actually calculate how many protons there are, right? Because 1 mole is 6.022 times 10 to the 23rd protons. 1 mole of protons. Right? 1 times 10 to the negative second is the same thing as, whoops, I did 1 times 10 to the negative second. 0.01. Right, because remember the exponent just tells you how many different places to move a decimal. So this is telling me to move a decimal 2 times, and it's also telling me to move it so that my number is smaller than 1. So 1.0, there's 1 movement, there's 2 movements. All right, so 0.01 molar solution, or 1 times 10 to the negative second. If I wanted to calculate just how many protons that were, I'd just do 6.022 times 10 to the negative, times 10 to the 23rd. And I could do times 1.0 times 10 to the negative second, but it'd probably be easier to just do this. And ultimately what that means is 6.022 times 10 to the 21st protons in 1 liter. right? So that's still quite a lot of protons. But just in case you math-brained people like going through the chemistry of this. If you're math-brained and you're chemistry-brained, I threw you a bone. You're not getting tested on molarity, hence why all of this stuff carries an asterisk. It means don't write it in your notes. Okay. Write it for fun, or if it helps you understand the entire concept. But ultimately, acids increase proton concentration. Let's get back to, this is hydronium. Let's get back to acid-base chemistry, because we just defined an acid. Now let's talk about a base. What makes a chemical basic? So, as a reminder, acids increase proton concentration. Just keep that up there. So what does a base do? Well, acids increase proton concentration. What could a base do? What on earth? How could a base work? I can't. That's right. A base decreases proton concentration. Right? If you put it in solution, and as a result of putting it in solution, the proton concentration goes down, well, guess what? It's a base, or it acted as a base. So, there's actually multiple ways that something could decrease proton concentration. You can have weak bases and strong bases. I'll start this out with an easy example that's a weak base, and that's ammonia. Now, the term weak in chemistry just means that it's a reversible reaction. It does not mean safe to drink. Let's not go out and start drinking ammonia because it's only a weak base. This is science vocab versus conversational English vocab. Yeah. So, ammonia, NH3. Ammonia is actually a fully satisfied compound. Nitrogen has fun with bonding angles. Right? And when you look at nitrogen, if you're looking at valence electrons, nitrogen on its own has 3 unpaired electrons and a pair. Right. So when you're looking at ammonia over here, NH3, it has that thing we talked about with hydronium, where you've got boop, boop, a pair of electrons right up here that look real comfy to a wandering proton. And so a wandering proton could chill out and use both those electrons to have a full valence. In which case, you'd have NH4. So, here's our proton plus NH3 gets us NH4, got a positive charge, and we call it ammonium. Right? As I said when we were talking about hydronium, this kind of covalent bond is not a particularly strong one, so it tends to be reversible. And the reversible nature of this is why ammonia is considered a weak base. So there you go. Not too bad. So ammonia can bind to a proton, become ammonium. And when it does that, there's one less proton in the solution. When one ammonia molecule binds to one proton, it becomes ammonium, and you have one less proton. Which means proton concentration decreased. Which means ammonia is a base. Ammonia is intrinsically basic because when you put it in a solution, proton concentration goes down. It's not like proton concentration goes down and bumps back up and goes down and bumps back up, because this is a reversible reaction. It still net goes down. You're not going to like put ammonia in there and then have it suddenly go back to as if there wasn't ammonia. But that's getting too far into the weeds. Got to stop myself. Okay, so that's ammonia, a weak base. We can see how it directly binds to a proton and decreases proton concentration that way. So we could directly bind to protons. And if you do that, this chemical reaction decreases proton concentration. Strong bases are hallmarked by what happens when they dissociate. So in general, strong bases produce a strong one-way reaction to remove protons. My example of a strong base is once again going to be something lazy and easy. All right, so we have our solution, and we're going to have our strong base, NaOH. This is sodium hydroxide. It is extremely strong. It is highly basic. You put sodium hydroxide in solution, and it will drastically decrease proton concentration very quickly. It's a very strong base. So, it's in solution, and it dissociates. And what we get is a sodium cation and a hydroxyl anion. If you have to answer some questions about bases or like alkaline compounds, same difference. Sodium hydroxide is like your go-to example. It's very easy, and it's also a very strong base. So, why is this a strong base? So far, just talking about the dissociation in water has not told us immediately why it's a strong base. But if you remember my water example, you probably see what's coming. And if you fast forwarded through my water example, that's fine. But let's talk about it. Ultimately, we're talking about protons. So, here's my concentration of protons, and they encounter one of these ions. Well, protons are positively charged and this sodium is positively charged, they're going to repel each other. They don't want to react. Like opposes like. You know, if I met me in a crowd, I'd probably dislike me as well. Who wants to be around that guy? He's loud and brings a lot of attention to himself. Anyway, the hydroxyl, negatively charged. Opposites attract. They will hang out. And what do you know? Here's 1H, here's 2H, H2O. So the proton and the hydroxyl bind and we get H2O. This is a very strong one-way reaction. You know, we're not going back to sodium hydroxide after this happens. You may have that weird water hydronium thing, but we're ignoring that. This is a one-way thing, right? You cannot run this backwards, get the proton, bind to the sodium, then get back to sodium hydroxide. That's what makes this a very strong base. Strong bases tend to release a hydroxyl, right? There's lots of different ways they could do this. Sodium hydroxide isn't the only strong base out there, but you can see it's got two little components. It's the easiest strong base to illustrate. But releasing a hydroxyl is kind of your big indicator of being a strong base. So, this is where I talk about ammonia, directly binds. For those of you interested, when a proton binds to a chemical that has what we call an isolated pair, like good old nitrogen, right? We call it a dative covalent bond. It has its own word. That was supposed to be a plus. So if that matters to you, if giving it a name matters, it is technically a covalent bond because nitrogen is sharing some electrons with this proton. So it's a dative covalent bond. So satisfies you. I want to know more, folks. Then we can donate it. Hydroxyl, sodium hydroxide. It's the alkaline compound in drain cleaner. When we talk about pH, you'll learn that it's a scale from 0 to 14. 14 is your measurement of like the strongest base on the pH scale. So sodium hydroxide, it doesn't take much to have, it doesn't take a whole lot of sodium hydroxide molecules in your solution to have something dangerously alkaline. So here's my fun thing about combining strong acids and strong bases. So let's say you have a chemistry set at home. And this isn't any chemistry set. Like, you have a chemistry set where you can control down to single molecules how much of a chemical you're adding, right? So you have 1 liter of water and you add exactly 1 mole of HCl, not 1 molecule more or less. Exactly. That's how fancy your chemistry set is. And you also get 1 mole of sodium hydroxide. Maybe you're going to do a Mr. Wizard demonstration, which, by the way, really dates me. Holy crap. That was some carbon dating stuff right there. Mr. Wizard. Anyway, it was a science show back when I was a kid. You get 1 mole exactly of HCl. You get 1 mole exactly of sodium hydroxide. You invite your friends over. This is highly concentrated HCl, highly concentrated sodium hydroxide. Working with this stuff in high concentrations is crazy. I was in an analytical chem class, and we had a really high concentration HCl solution that we used in order to make our own dilutions of it. And when you added HCl to a beaker, you had to hold that beaker at an angle, because when you opened it so that it would drain slowly, and you had to drain it very slowly, as it poured down the sides and pooled in the bottom, the whole beaker heated up. Like, that's some dangerous stuff, man. Anyway, you pour that concentrated HCl on like a shoe, and it bubbles, and it's a violent hissing reaction, and you can see the shoe leather burning away. People are like, oh, geez. You take your sodium hydroxide, you pour that onto shoe leather, bubbling, hissing, burning. Oof. Ooh, that seems dangerous, all right. You probably shouldn't be handling that. And then you have this gigantic beaker, right? And you have these 2 little grippy things that you put the 2 solutions in. And then you stand behind a shield, and you like pull a lever, and the beakers turn, and they combine this stuff into one giant beaker, and there's this massive, violent reaction, right? When 1 mole exactly of hydrochloric acid meets exactly 1 mole of sodium hydroxide. Violent reaction. Heat. Maybe the glass beaker breaks a little. Who knows? Like, it's crazy. And once it's done, right, stir that solution a bit more. Then you dip a drinking glass in there and you say, here's to you, pals, and you drink it. Everybody's like, wow, stop, no! And what happens to you after drinking a mixture of those 2 highly dangerous solutions? The answer is you go, ooh. Because when you combine a strong acid and a strong base, something kind of cool happens, right? Here's HCl. And it dissociates into protons and chlorine. And here's sodium hydroxide. And it dissociates into sodium and hydroxyl. Well, as we just knew from my explanation of sodium hydroxide, right, when a hydroxyl meets a proton, whoop, you get water. Well, look at what's left here. Positively charged sodium, negatively charged chlorine. Where have we seen that before? Boop. When you combine a strong acid and a strong base, if it's at a low, it produces water and salt. So salt water. You get water and you get some kind of salt. In the case of sodium hydroxide and hydrochloric acid, it's table salt. But one of the hallmarks of making combining a strong acid and a strong base, you always get salt water, which is pretty darn cool. If you have that level of chemistry set at home, where you're able to measure down to the proton, how many protons are in a solution, and how many sodium hydroxide molecules are, if you're working at that level of precision, you're probably Breaking Bad. So I don't know, it's probably more profitable to just continue making meth rather than do cool demonstrations. Anyway, now let's talk about how we measure the strength of acids and bases. And remember, it's all about proton concentration, right? Well, a neutral solution has neither acidic nor basic properties. The proton concentration required to have neither acidic nor basic properties is a proton concentration of 10 to the negative 7th. So, 10 to the negative 7th. That's the concentration of protons to be neutral. Right? Or 1, 2, 3, 4, 5, 6, 7. Right. This number of moles of protons in 1 liter of water. Again, the exact math doesn't matter, but this whole 10 to the negative 7th thing matters. Like the exact math on moles, and 6.022 times 10 to the 23rd. That doesn't matter. But I've got a lame joke at the end that will involve moles. Because... Okay. So, if you have a concentration of 10 to the negative 7th of protons in 1 liter of water, then ta-da! If your concentration is 1/10,000,000th moles per liter of water, then what you have is a neutral solution. Like a liquid that is only molecular H2O. Like there's nothing else dissolved in it. That's really, really hard to get a hold of. The closest you can get is something called milliQ water. Now that you're going to need to test it on that. But most chemistry labs don't even bother making milliQ. So anyway, fewer protons means you're basic, right? So if we're looking at numbers on a number line, right? Here's higher, here's lower. We're just going to set basic or neutral in the middle, right? 0.023, 4, 5, 6, 1. Fewer protons than this means you're in a basic solution. 10 to the negative 8th is fewer, right? Just for those of you who don't remember number line stuff or, don't remember this kind of thing, that's one more decimal over. 1, 2, 3, 4, 5, 6, 7. And if I put it here, that's 10 times fewer protons. So if you have less than 10 to the negative 7th moles per liter, then you're a basic solution. If you have more than 10 to the negative 7th moles per liter, you are an acidic or alkaline solution, right? So here's 10 to the negative 6th. And if we were to put it up here, you can see 10 to the negative 6th is a number that is 10 times larger. So, fewer protons means basic. More means acidic. Is that easy? Acids are everywhere. Gastric acid, bases are everywhere. So I don't have examples of bases in biological systems offhand, but I can tell you that the pH of blood is 7.4, so slightly basic. The pH of the fluid in a cell tends to be somewhere between 7.2 to 7.6, so slightly basic. Important organic compounds. Especially proteins. They can fall apart in different pHs. So in too acidic or basic environments. So the acidity or alkalinity of the environment has huge concentrations on whether or not a cell can remain alive, right? And then, of course, if we're talking about huge importance when looking at pancake batter, buttermilk is acidic, and NaHCO3, sodium bicarbonate, baking soda, is basic. And that's the way you get your carbon dioxide bubbles in pancake batter, and that's why your pancakes are fluffy. So possibly even more of important an example than everything I've said so far. Okay, so let's talk about the pH scale. When we talk about how acidic or basic something is, we will often talk about the pH. pH scale measures the strength of an acid or base. So, how strong an acidic or basic solution is. The pH scale is surprisingly easy to understand. It is literally just math based on proton concentrations. So, you calculate your proton concentration. You can, like in modern science, you often have a little computer and a probe. You just insert the probe in the solution, and I think it uses like conductivity or something, but it kicks out the proton concentration. So that's nice. Way back when, you'd have to use like really, really precise chemistry sets and know the exact like molarity of solutions you started with and volumes you added and stuff. But either way, you could actually get your proton concentration. And once you have your proton concentration, your moles per liter, you get out a calculator and you do a negative log of the proton concentration. Right? We know pH 7 is neutral. It's just one of those things most people seem to know from various aspects of their life growing up. pH 7 is neutral. We also know from a slide I just talked about that neutral is a proton concentration of 1 times 10 to the negative 7th. Well, guess what? If you do a negative log of 1 times 10 to the negative 7th, or this is 1.0 times 10 to the negative 7th. The number you get is 7. It's literally the negative log of the proton concentration. This is why as you go lower than 7, it's acidic, and as you go higher than 7, it's basic. Because if you have fewer protons than neutral, the solution becomes acidic. If you have fewer protons than neutral, the solution becomes basic. And if you have more protons than neutral, the solution becomes acidic. It's that easy. It's that simple. Neutral is a solution with a proton concentration of 10 to the negative 7th. All right, 10 to the negative 7th moles per liter. If you had, yeah. Anyway, acidic solutions have more protons than neutral solutions. Basic solutions have less protons than neutral solutions. Neutral has 10 to the negative 7th protons. It's that easy, man. So, proton concentration logarithm is negative log. Blah. It's that easy. So, when you're looking at proton concentrations, oftentimes we talk about pH 1 as the minimum and pH 14 is the highest, but technically you can go down to pH 0. This is just a convenient thing with some fun examples, right? So your stomach lining secretes gastric acid at HCl concentrations that would measure out to a pH of 1, right? When they're mixed with everything else in there and water, then your gastric acid goes to about pH 2. So not too bad. And this is just cool examples. So you can see that if your stomach lining can handle gastric acid, then it can also handle anything at that pH or above, until you get to things that are pretty basic, at which point things get dangerous again. But there you go. When looking at the concentrations of protons, right here, ignore this thing on this side. That's a bad indicator. I prefer the one with the exponents. It just makes more sense. So there you go. 10 to the negative 7th, a concentration of protons that's 10 to the negative 7th is pH 7. Right? pH 6 is 10 times more protons compared to 7. pH 5 is 100 times more protons compared to 7. Right? 1,000 times, 10,000 times, 100,000 times. pH 1 has 1,000,000 times more protons than pH 7. That's what, so that's what this little thing here was doing that I scratched out. That was showing the relative amount of protons to pH 7. But anyway, pH 8, 10 to the negative 8th, so 10 times fewer protons. All the way to 1,000,000 times, 1/10,000,000th, I think, whatever. Yeah, 10,000,000 times fewer protons than pH 7. And it's literally just proton concentration. All right, this brings us to the final subject of this lecture in the last 3 slides, and that's buffers. Buffers are a type of chemical vital to living things, right? When you think about it, I say blood has a pH of 7.4. How does blood stay at a pH of 7.4? It's not like everything you put in your body and digest is pH 7.4. If I drink lemon juice, that's pH 2, right? So how does blood stay at pH 7.4? And the answer is buffers. Nothing you eat or drink can alter your blood's pH. Nothing you eat or drink can alter the pH of the tissue that makes up your body. That's because pH is maintained from buffers. Buffers are a type of chemical that can do 2 things. They're capable of doing 2 things. If you can do these 2 things, congratulations, in chemistry, you're a buffer. Those 2 things are directly bind to protons and release bound protons. That's it. These 2 things, if you are capable of doing these 2 things, you are a buffer. And if you are a buffer, one of the neat things that is the neat behavior here related to these two things is that you maintain a specific proton concentrations. Buffers maintain specific proton concentrations. All right? So what that concentration in is depends entirely on the buffer. Like all the natural buffers in the universe, they have different proton concentrations that they maintain. Limestone in caves is a buffer. I do not remember the proton concentration that limestone maintains. But like that's just a natural buffer. You can dip into a limestone cave and you found buffers, right? There are blood buffers to maintain 7.4. There's also your liver and your kidneys to maintain 7.4, but blood buffers are a very important component of maintaining 7.4. So, buffers maintain a specific pH. So, here, let's say you've got your buffered pH, and why not 7? Because I'm lazy and neutral makes sense to people, right? I've got my solution buffered to pH 7. I threw a buffer in there that naturally maintains pH 7, right? Just due to the chemistry of that particular buffer, it maintains pH 7. How does it do that? Well, when the solution is at pH 7, your buffer is just chilling, dissolved in there, floating around, living its best life. But if I add a proton, I've just increased my proton concentration, and my solution is going to become more acidic, right? It makes the solution more acidic. Now my buffer kicks into gear, right? Increase in the proton concentration is just due to the laws of physics and chemistry for this particular buffer. It causes this buffer to bind to the proton. My pH 7 buffer, and we're just using pH 7 because it's arbitrary and neutral and people's brains like that. It binds to the proton. And so we go right back to neutral, right? We added a proton, it became more acidic, the buffer bound to the proton, yanked it out of the solution, and we went right back to neutral. We're back to our homeostasis pH. Right? Well, what happens if you add sodium hydroxide and we lose a proton, right? We lose a proton. Well, proton concentration just went down by 1 proton, so the solution becomes more basic. Right? Due to the physics and chemistry of this particular pH 7 buffer, this causes it to release a proton. Not getting into too much detail, all these buffers are capable of releasing protons even if they haven't bound to any new ones. Right? They just have a reservoir. So the buffer releases the proton, and we lost a proton, the buffer releases a proton, back to homeostasis. And that's how a buffer do. It's that simple. A buffer can do these two things. It can directly bind to protons, and it can release bound protons. And depending on the chemical makeup of your buffer, when the pH goes, when the proton concentration goes above that buffer's homeostasis level, the buffer directly binds to those protons, yanks them back to homeostasis level. When the number of protons goes below homeostasis level, the buffer releases a bunch of protons, brings it right back up to homeostasis level. That's it. That's buffers. It's not the worst thing on the planet. They're very cool. So, my favorite example of buffers is the blood buffer, because it's extremely important, right? Blood pH is 7.4. If it goes below 7.4, right? If it goes more acidic than 7.4, or it goes more basic than 7.4, then bad things start to happen, right? You hit acidosis. This is a condition where the tissues of your body are being exposed to unsafe levels of acid, and it starts to damage and destroy tissues. So any tissue that's in contact with your blood is now getting damaged and destroyed by the pH of your blood because it's less than 7.4. And that's bad, because that's like almost all of your tissues. Like, I guess your cartilage is safe. So acidosis is bad. Once you hit a certain pH, your body tissues basically like get super dead. And in fact, the whole you dies. Right? You are now dead. If your blood pH drops to this level, you're dead. If it goes above 7.4, congratulations, you're now in alkalosis. And you have hit dangerous levels of alkalinity. And it's damaging the tissue that's in contact with your blood. That's almost all of your tissue, except your cartilage is probably safe. And that's bad. And if it becomes too basic, congratulations, you're dead. Right? And so the question is, what range can your blood go outside of 7.4 before you as an organism are dead? Right? Before the blood pH is causing irreversible damage to your organs and you hit organ shutdown and you die. Right? It's destroyed your marrow, it's destroyed your kidneys, your liver, like you've suffered widespread organ damage and you are dead. And the answer is neutral. If your blood pH goes as low as neutral, or becomes so acidic that it's neutral, you're dead. And because we love math that just feels good to write, 7.8 is the death point for alkalinity. A 0.4 in either direction will murder you. And this is why those blood buffers in concert with your liver and your kidneys are so important. This is also why there's nothing you can eat or drink that could alter the pH of your blood. Right? You cannot affect the pH of your body with your diet. If you could affect the pH of your body with your diet, you would be dead, because it's a 0.4 shift to kill you. I mention this because there was a big trend a long time ago to eat an alkaline diet. They were like, "Oh man, all your problems are because your body's acidic, bro. Why you have that cancer? Your body's acidic. You got migraines, bro. Your body's acidic. You've got autism, bro. Your body's acidic. You should eat an alkaline meal." And it got real dumb. Like, it got real dumb. You're not like tested beyond here. Besides the fact that, like, if you want to talk about why buffers are so important, this blood example is great. You're not going to get tested on this really dumb pseudoscience diet. You can still see it, though. Alkaline water or black water, those are both products that were originally marketed for the alkaline diet. So, but yeah, like, how do you make your diet more basic? You eat chicken, lots of vegetables, and rice. And amazingly enough, when people went on the alkaline diet, they started to feel better because they stopped eating so many Snickers bars and ice cream and started eating chicken, rice, and vegetables. Who could have guessed that decreasing your calorie intake and eating a more nutritionally balanced diet would make you healthier? That couldn't be it. It had to be alkalinity. That's what it was. They got that trend got so dumb that it became universally known amongst the people who bought into it that if you drink lemon juice, pH 2, it will make your body more alkaline. How? Because lemon juice goes into your stomach, yada, 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 body becomes more alkaline. That was the extent of the science justifying lemon juice making your body more alkaline. But yeah, literally, you cannot alter the alkalinity or the pH of your blood through what you eat. So you're more likely to, like, drink something so acidic that you directly kill yourself than ever get to the point where your blood pH is affected. Blah, 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 buffers. And these blood buffers help in good old homeostasis. Enzymes and reactions often, we'll go into enzymes later, but basically enzymes are associated with the chemical reactions that, make you living. And the pH of the environment can directly affect those enzymes. Enzymes are a type of protein. Proteins can fall apart if the environment becomes too acidic or too basic, relative to their homeostasis, natural pH. So those enzymes that allow the reactions that keep you alive to occur at a high enough rate to keep you alive fall apart if the pH goes wrong and you die. So again, buffers, very important. Different things are maintained at different pHs. Gastric proteases, fancy word for enzymes that control the reactions that digest protein in your stomach. And they are activated at roughly pH 2 because gastric acid. And they are deactivated when the pH goes above that. And when that acidic mixture of food from your stomach gets dumped into your small intestine, the very, very, very first part of your small intestine, connected to your pancreas, releases a bunch of juices. One of the things in that juice is sodium bicarbonate, which basically buffers you back up to the proper pH for your small intestine. So, and once it does that, it deactivates all those proteases, which is good because body tissues are made up of tons of protein. And if those enzymes that allow protein to be digested were active in your small intestine, you would digest your own small intestine. And that's, I believe the medical term is bad. Platelet enzymes, which allow your blood to clot, function at pH 7.4. pH goes too far outside of that, and they break down, and suddenly you can't clot. And that is also bad. So,